Tian from Beijing University and Princeton University. Well, as you probably know, Tian is widely known in the community for his many contributions in the field of geometric analysis. So this is his second time here in Brazil. I came here in 2007 for a whole month. So yeah, and the title of his talk is Recent Progresses on Kähler-Einstein Metrics.
Thanks. So it's thanks for invitation, and it's a pleasure to come back and to talk in this Congress second time. So what I'm going to tell you is some a little bit on some recent progress on Kähler-Einstein metrics. So let me start with some general things. Okay, a basic problem in differential geometry is to study how curvature interacts with geometry and topology of underlying spaces. So this needs to study canonical metrics on a given metric, on a given manifold. So let's start with some simple known things. So by classical uniformization theorem in complex analysis, we know that each Riemann surface is a quotient of a standard space. So these standard space are two-dimensional sphere, or Euclidean space, the plane, Euclidean plane, or the hyperbolic plane, the Euclidean disk. So it follows any Riemann surface admits a metric of constant curvature because all these standard space, each of these standard space carries a canonical metric. So it can write down a good metric on that. So there's there's other approaches to establishing the same fact. The one I told you before is like approach by using a complex analysis. So there is a more recent approach. It's more geometric, more analytic. So, for example, I'm giving any metric on a two-dimensional space, and one can associate a conformal structure. So that basically is giving a metric. You can measure the angle between two vectors at each point. So that's give you a conformal structure. So if you deform the metric in this way, and by simply multiply by some positive functions, so this way does not change angles because it's just a scale metric at each point. So in particular, it preserves a conformal class. So, but you do this deformation, you change a metric this way, and you expect you want this new metric to have a constant curvature, which is given by a function, right? So curvature in two dimensions is given by a function. So the simplest function is a constant function. So we want a metric with a constant curvature. Okay. So that's as I said on previous transparency, we already have the metric with constant curvature, but due to some other facts. However, if I don't know the topology, I don't have I just give a space, and I do not have this Riemann mapping theorem or these things before. So we try to try to solve the differential equations. So if so this new metric is of constant curvature if and only if this function u satisfies the following semi-linear equation. The semi-linear equation. So this G0 is a curvature of a given metric. G0 is given. Okay. Now u is unknown. The lambda is constant. It's constant of Gauss curvature of this new metric. So this is a semi-linear equation. So Laplace here is just Laplacian of G0. Okay. If you can solve this equation, and then this one has a constant curvature, so then you can also lower. As a consequence, you lower the topology of underlying space. So this path is a bit different from what we said before. So So you just solving an equation blindly, and you get a solution, if you're lucky, and then you get geometrical consequences. So this equation has been studied a lot since late 60s by many people, okay? Like Nirenberg, Kastan, Waller, and Obang, so on. Okay. So it can be also solved by using a Ricci flow, studied by Richard Hamilton, and so on. So as a consequence, I said, is that every compact Riemann surface admits a metrical constant curvature, and within a given conformal class. Okay. So this is at the beginning I don't know the structure of a Riemann surface, and I just try to solve the PDE, the semi-linear equations. And what about the high dimensions? So in high dimension, instead of making the curvature has more components. It has more components because we have more directions. So instead of solving a previous equation, we consider so-called Einstein equation. So we say G metric is Einstein if the Ricci curvature is a multiple of metric. So Ricci curvature is only part of a curvature. It's part of a curvature. It measures the deviation of volume form from a Euclidean one because the space is curved now, and you don't expect volume form stay the same. So when you do integration, the volume form may change from point to point, and that's change if you and is reflected by a Ricci curvature. Okay, so in dimension 2, any Einstein metric is simply a metric of constant curvature because in dimension 2 there's only one curvature component. All the curvatures are the same. Okay. So this is a picture, I guess, a picture to illustrate the role of Ricci curvature. So this is a volume form at the nearby point, and this is a volume form at the given point P. So that's a deviation measured by Ricci curvature. Okay. So if Ricci curvature is 0, basically, in some sense, the volume form stays the same. So there are two important cases of Einstein equation. So before that, maybe I should make a statement because in this talk, or at least in differential geometry now, we are considering an elliptic case. Namely, we consider Riemannian metrics. So original Einstein equation works in the Lorentz case. So it's a hyperbolic system. So now we are only looking at the static solution of that. So there are two important cases of Einstein equation, at least the Riemannian case. So one is when the M is a 3-manifold. In this case, any Einstein metric is of a constant sectional curvature. So then Thorsten geometrization conjecture states any 3-manifold can be decomposed in a lateral way into these Einstein 3-manifolds plus some graph manifolds. So there are 8 kinds of geometries. So Einstein equation has in some sense dimension 3 has 8 kinds of solutions, and the 3 are non-degenerate, and there are 5 other types in some sense degenerate because they are actually live on a smaller dimensional space, okay? Of a space of smaller dimension, so-called graph manifold. But anyway, this because of the special structure and topologically these spaces are well understood. So maybe the most difficult part of these 3-manifold is so-called hyperbolic spaces. Okay. So a conjecture was solved by Berman using a Hamilton Ricci flow. So it's not what I okay. So what I'm going to talk today is another case. So before that, I should say it's of course there are many works on finding a solution of Einstein equations, and so there are many beautiful works. And so why I say this, I singled out these 2 cases simply because those 2 cases we have a more comprehensive solutions, more complete solution of a problem. Okay, and they both, in some sense, are a generalization of a 2-dimensional case. So in many cases in geometry, we start at 2 dimensions and try to understand it in a different way. and then you branch out to see what we can do in the high dimensions. Okay. So 3 dimension is one case, and we do know a lot. I mean, we do quite complete now because, for example, social geometric conjecture has been solved. Okay. So other case is called Kähler case. Kähler case. So this means M is first is a complex manifold together with a Kähler metric. Okay. So Kähler metric locally. So first is complex manifold. So locally you can give in by complex coordinates. And the metric is giving since it's complex coordinates. So you can the natural class of metrics you want to consider is given by Hermitian positive matrix valued functions. So in general, Riemannian metrics are locally given by positive definite matrix valued functions. So because of a complex structure here, we impose the Hermitian conditions, okay, to make a more constraint on the matrix. So convenient way to write a matrix is to write in terms of 2 forms, so-called Kähler form. So this GI, J bar, and so on. And this is a global defined 2 form. But there's in general, this metric is only called a Hermitian metric. And this is still quite a large class of metrics. And of course, you can still try to solve the Einstein equations within the class of Hermitian metrics. And that's still very hard to solve. So we impose one actual condition, so integrability condition. So this condition basically says locally. So this condition is equivalent to say, so locally, this Gij bar is given by a derivative of 1 functions. So locally, the freedom only is given by 1 functions. So that's why in the Kähler case, so that's what we call the Kähler metric. That's why in the Kähler case, since Einstein equation is easier to solve. Okay. So we say omega is Kähler-Einstein. If it's Kähler, so it's a metric of this type. Locally, is given by functions. Okay, and it's also said for Einstein equations. So lambda is normalized. Modular scaling is normalized as one of these 3 cases. So for Riemann surfaces, so this corresponds to hyperbolic case. This corresponds to Euclidean space. This corresponds to Riemann's fields. Okay. So being a Kähler metric, another thing is good is being a Kähler metric. In a local coordinates, the Ricci curvature is given by this. So you can immediately see this is Ricci curvature is determined by determines a Warning form. Okay. And then you can roughly see from this equation here, and the local is given by a derivative of Warning form, a logarithm for determinant of metrics, and omega locally given by functions. So at least locally, to solving this Einstein equation in this special case, it's like solving some scalar equation of Montrompe type, okay, of determinant equal to something. Okay, that's how. So this makes things be easier. So in the 50s, Calabi started the study of Kähler-Einstein metrics on a compact Kähler manifold. A necessary condition you immediately see is M has a definitely first Chern class. So that's because this in the previous case, this is Ricci curvature is closed. Ricci curvature as a form here is closed because it has this thing. But I warn you, this Warning form here is locally. So this is not the exact form. It's locally exact, but globally it's still carries non-trivial topology. That's actually just a first Chern class. So that's some necessary condition. So uniqueness was proved by Calabi in the 50s when first Chern class is less equal to 0. That corresponds to a case when the lambda is -1 or 0. Okay, so uniqueness of this equation was solved by using a maximum principle. Okay, so So when the lambda positive the case was much harder because you cannot directly apply the maximum principle. So that was not done until 1986 by Bando Mabuchi, two Japanese mathematicians. So the existence, there's this in the case when the lambda is negative, -1, that was done, proved by Oba and Yao independently in 1976. When the lambda is 0, namely the first Chern class is 0, was solved by Yao in his famous Calabi solution of Calabi conjecture. Okay, so since then it remains to show the existence of Kähler-Einstein matrix when the first Chern class is positive. So this is so this corresponds to if n equal to 1 case. So I said that this C1m positive corresponds to a case when the Ricci curvature of a metric is this. So this is the equation you want to solve. Okay, and this is a necessary condition, some integrable condition to guarantee you can do that. So n equal to 1 case, this is the underlying manifold is just S2. Just S2. Okay, so nothing interesting. But when you dimension bigger than 1, actually there are still many cases. Even though this is compared to other cases, this the positive case there are few positive manifolds than negative manifolds of manifold negative curvature, negative first Chern class, but still there are a lot. Okay, so this called so this class of manifold called the fellow manifolds. So give a name because the fellow and the Russian mathematician fellow classified the three-fourths case. And n equal to 1 case, that's nothing to clarify. That's just Riemann's field. But n equal to 2, the Italian geometer did in early 20th century. So they actually have for n equal to 2 case, there are basically 8 kinds of them, or 9 kinds of them, and 9 classes of them. And they call it their Peso surfaces. They classified by follows from Italian geometry, the work of Italian geometry school. Okay, and a fellow classified three-fourths and the case for n equal to 3. Actually, he missed some cases I will mention. Okay. So at n equal to 3 case, actually the number increases. So actually there are 81, more than 81 family of these fellow three-fourths. Okay. So first thing is not every fellow manifold, namely this is a class of manifold with positive first Chern class, admits the Kähler-Einstein metric. So there are new abstractions to our existence. So one abstraction was already known in the 50s, 57. It's an automorphism group for M being reductive. So let me state it. So if a manifold with positive first Chern class admits the Kähler-Einstein metric, then its automorphism group has to be reductive. So that's a special property for group. And you can easily find the example, even n equal 2, even for the case n equal 2, there are Peso surfaces with whose automorphism group is not reductive. Okay. So they do not admit the Kähler-Einstein matrix. So what more closely relate to today's things is called the Fataki invariant in the 83. This is a character on the algebra automorphism group. It's like an extension of Carsten-Waller invariant. Okay, so in an n equal to 1 case, you can think this is a case of like Carsten-Waller invariant. And so what is a Fataki invariant? So it's a character from the algebra. So what is this guy? This is just all the algebra of all holomorphic vector fields on M. Okay. So it can be defined as follows. The definition is so this is actually original definition. It has some advantage. Later on, there are some other way of defining this. So let omega 0 be a Kähler metric with this Kähler class. So this is some constraint because Kähler metric is closed, so it represents some cohomology class. So you do this normalization. Okay. So then you define this, and H0 is chosen by this, and this is possible is because of this condition, and this is up to a constant, so you normalize this. So this you solve this equation, but it's not unique because up to some constant, so you normalize this constant by these integral conditions. So what Fataki proved in 83 is this Fm does not depend on a choice of omega 0. Okay? So long as omega 0 satisfies this condition, and you do this process, you get the integral, but the integral does not depend on a choice of a metric. Okay? So even though the way of defining this integral itself looks like it depends. Okay? So in particular, he proved this is invariant because if this is independent of choice of metric, then you immediately see if M admits a Kähler-Einstein metric, that means if you can choose omega 0 to be Kähler-Einstein, so this side is 0, so H0 is constant, so then this integral is 0. Okay, so that means so this is abstraction. So and he did give examples where this invariant is not 0. It's not 0. So those examples do not admit Kähler-Einstein metrics. Okay. So this already said that. So I guess in the complex in the angle 2 case, this is only abstraction. Fataki invariant is only abstraction because in many years ago I proved that if a complex surface M admits a Kähler-Einstein metric if and only if Fataki invariant vanishes. Okay. But for long, the only abstraction arises from the Lie algebra. So this led to a speculation is if a Fano manifold has no non-zero holomorphic field, then M admits a Kähler-Einstein metric, and it turns out this is not right, and it's probably we already realized this is not quite right for long, but didn't know how to do it. So eventually we be able to prove it by using these case stability things. So this is a new set of it's a new abstractions we found in the 90s. So to say that the case stability, let me remind you of some very classical theorem in a complex geometry or in algebraic geometry. You can see one of the famous Kodaira theorems says if for L sufficiently big, so actually Kodaira theorem covers more cases, but since let me just consider the case. In our case, the manifold is a Fano manifold. So this is a notation. Maybe it's a remind. So this is just determinant wedge of a holomorphic tangent bundle. So it's become a line bundle. Okay. So C1 positive simply says that this line bundle has many sections when you raise the tensor pole. Okay. So K guess minus L is a notation. So you twist it itself several times, L times. Okay, so Kodaira theorem says if L is sufficiently big and this cohomology group has many sections, and you take any basis of that to give you embedding. So you can embed your manifold into projective space which becomes an algebraic manifold. So we may consider M as a subwriting in CPN. Then for any algebraic subgroup G0, so this is automorphism group of that. So there's a unique limit cycle. Okay. So in the 1992, Dean and I generalized the Fataki things. So what we actually did is just make sure this Fataki's definition integral still makes sense even the M0 has some singularities. Okay, so if M0 is normal, so that means singular set is that implies a singular set is small. It's of a complex codimension at least 2. Okay, so in that case one can associate a generalized Fataki invariant. So that's exactly as we define. So maybe to be simpler, it just says so. What I did with Dean is simply says a Fataki invariant can be defined on singular varieties if a singular set is not very big. So then we say M is called stable for air if this one is big equal to 0 for any this. So normally this is a complex number, but there are some invariants. Actually, this takes a real value, so you can talk about this. So anyway, so let's don't go into too many details. So with a normal M0, and the equality holds if and only if M0 is biholomorphic. Okay, so M is k-stable if it is a k-stable for all the sufficiently large air. Okay, and later on, Donaldson gave a more algebraic formulation of this, which is more friendly to algebraic geometers. Okay, because the Fatakis or what I did with Dean still use the integrals and is some more analytic. So just to remind you, so this invariant is not necessarily on the original manifold. Is on some limiting cycle, which is related to this M. So M itself may not have holomorphic vector fields, but M0 does. Okay. So using this, we found proved if I proved in 1996, if M has a fellow manifold without holomorphic vector fields, then M admits a Kähler-Einstein metric only if M is k-stable. So they are fellow manifold, fellow threefolds without the non-zero holomorphic vector fields, which are not k-stable. So they do not admit Kähler-Einstein metric. Actually, the example I found I used was it's not due to me. It's due to Mokai and Umamura, and it's also related to this carbon 60. This it's actually the SR2C quotient by icosahedral group. Then you take a certain complication. Okay? And this threefold is not maybe I shouldn't call it fellow threefold because that was a threefold missed by fellow in his classification. So it's not found by fellow. So anyway, the K stability can be also defined for more general cases. So not necessarily for this particular class of Kähler manifold, and Jacob Stoppa generalized the Ball theorem to more general cases in about 6-7 years ago. So then the conjecture is if M is k-stable, so air now this time is more general, then M admits a Kähler metric of a constant scalar curvature and with the Kähler class, if this is k-stable. Okay. And the other way is already proved by Jacobs. Okay. So today we'll talk about this case when for fellow manifolds. So if M is k-stable fellow manifold, then the M admits the Kähler-Einstein metric. So this is the inverse, converse to the theorem I proved in 1996. So this particularly solved this conjecture in the case of fellow manifolds. So four conjectures still open. It's still open. Okay, four conjectures still open. So alternative proof of this was also claimed by Tian and Donaldson and Song. Okay. So how to prove existence of Kähler-Einstein metrics? Okay, so I'm not going to show you a whole proof because it's quite long. So I just show you main ingredients, two main ingredients. So before that, let me remind you a bit why we can do to establish the existence of Kähler-Einstein matrix. So M admits a Kähler-Einstein matrix if and only if one can solve this equation. Okay? So this follows from this basically this fact here. Okay? So this fact, so this is equivalent to the Kähler-Einstein equation, the Einstein equation in the case of Kähler matrix, and it's because of this. Okay? So in general, there's a lambda in front of phi here. The lambda here, in this case, I take is just lambda equal to 1. So that's on remaining case we need to worry about. But for like Yao, Calabi-Yao theorem, in the case of Calabi-Yao theorem or in the case of Obang-Yao theorem, there's a lambda here. Lambda is -1 or 0. Okay, 0. So in general, so in order to do that, basically we want to solve this equation. Okay, and in the as I said, in the case of Obang-Yao and Calabi-Yao, it's the corresponding equation is solvable. Okay, because change of sign here will make things make certain things easier. Okay, so in general, it's not solvable in this case because of obstructions, right? So one approach to establish existence is Obang's continuity method. So what Obang suggested in the 83 is actually this. I should say this continuity method was known for. I mean, continuity method was used to solve this kind of problems. Was known for a long time, but for this particular case, this was Obang who wrote down this. So this he put insert t in front of that. So you let E to be a set of t between 0 and 1, such that above equation is solvable. Okay, and 0 is certainly in the E because of Calabi-Yao theorem. That's already done in 1906 by Yao. So follows from Yao's theorem, for Calabi conjecture. So E is what Obang's observation is basically is E is open. E is open. So in 83. So the number of t such that the set of t such that this is solvable is open set. So to have a valid continuity method, this is basically crucial to have openness. Otherwise, you don't know how to continue path. You get some point, you don't know whether you can go further. Okay. So then also using an Obang-Yao second order estimate. Before that, I should say, in order to say if 1 is contained E, then the previous equation is solvable. Okay. So whole thing remains. It remains to prove the E is closed. So for this, all this continuity method, and the most technical part is to prove E is closed, and this is amount to establishing certain a priori estimates of a solution of equation of this type. Okay, so fortunately, using an Obang-Yao second order estimate, the Calabi third order estimate, one only needs to show the C0 estimate. So then what I mean here is if you can bound the solution of this equation a priori in C0 long, then you can bound all the high order derivatives. Okay, so and such a C0 estimate you can further reduce. So for nonlinear equations, there are always some critical norm, and you want to establish it. Then after that, it becomes could become known. Okay, so such a theory follows from a properties of Lagrangian. So it's actually you can even reduce a weaker norm. So this is complicated, but it's easy to remember. Don't need to remember everything. So this is simply a Lagrangian of this previous equation, this equation here. Okay. So this is a variational problem, even though this is a fully nonlinear equation. But this is a variational, and the Lagrangian is exactly this. And here is basically Lagrangian of Monchampel operator. Okay, complex Monchampel. So proper simply means what? Means so giving a function, giving a function on a 5-dimensional with a 5-dimensional domain, the proper means the pre-image of bounded interval is a compact set. So all you say is a bounded set, and you just adapt this definition to all the infinite dimensions. So if that space has certain norms, and the norm can be just given by this. This is positive. Okay. So anyway, in the early 90s, I proved that if M has a non-trivial, if M has no non-trivial holomorphic vector fields, then the M admits a Kähler-Einstein metric if and only if this is proper. So namely, if this functional stays in the bounded things, then the corresponding function will stay in the bounded set. Okay. So in a certain norm. So it's the basic energy norm I didn't write down. So the K stability is closely related to these properties. So K stability is actually just like the properties of this functional in the 5-dimensional case. So to see that, I just back to Kodaira theorem again. So previously I already said by Kodaira theorem says any basis of this gives an embedding. So you can think M as a submanifold inside some projective space. So then we get a family of metrics. So this is a homogeneous metric on the CPN, and you pull back, and before you pull back, you can always use automorphisms. So 1 over L, this normalization here, just make sure this Kähler class stays in the first-term class. Okay, stay in the first-term class. So you get family of metrics. So this family of metrics is all determined by this automorphism here. Okay. So tau is in the SL n plus 1C, which is basically automorphism group of CPN. Okay. So what I proved in the thesis is if you take L sufficiently big and take a union of this is dense in the space of Kähler metrics. Okay, so with the given Kähler class, and the K stability simply corresponds to the properties of this restricted 5-dimensional space for sufficient large L. So I did give you like this algebraic definition in terms of one-parameter subgroups, algebraic subgroups. That's more like algebraic definition. Okay, so in the geometric invariant theory, so you can define a so-called this manifold stability, and which corresponds to certain properties of functionals. But still, this is you want to have a easier, or at least some criterion to check that. That's called so-called Hilbert manifold criterion. So namely, you detect these properties. You just want to check these properties on a one-parameter subgroup. That's good enough. Okay, because so then you only need to check a few things. Okay. So maybe I'll give a bit more details about these previous things. So for any omega with Kähler things, induce the inner product on this. So Kodaira theorem does not involve any metric. So now with metric, we try to refine Kodaira theorem. So that's actually what I did in the previous transparency. So let this is orthonormal basis with respect to this inner product, and plot these things. Okay, square sum, and this is a function. And this function depends only on omega. It depends on Kähler metric. So what I did in the thesis says this, you normalize this function is converged to positive constant determined by Riemann-Roch. And this implies the previous density theorem. So this actually implies this density theorem. So for each fixed omega, you let L goes to infinity, this goes to constant, this goes to constant, it goes to constant. And the constant can be determined by some topological, it has some topological meanings. Okay, so So in view of this, and a certain compactness theorem, I made a conjecture a long time ago, and it turns out this is a crucial part in the proof. So they are constant, depending on certain dimension and k, such that for any omega within a Kähler class, given Kähler, this is some normalization, so, and the reach curvature bigger equal to T0, and this is bounded from below. So what's the relation between this and the previous one? So I said if you fix omega, let L goes to infinity, it always goes some positive constant. In particular, these things is always bounded from below by some positive constant times L to n. It's not only bounded from below, it's actually very big, one L. But since here, this convergence may depend on omega. So only thing I want here difference is I want to be uniform on omega. And of course, that's you may not be true if you don't impose a condition on omega. So the condition imposed on omega is there are some curvature conditions. Okay. To make this a bit more understandable, let me start with even the Riemann's field case. It seems to be still a non-trivial theorem. So Riemann's field case, So you can identify Riemann's field as a complex plane with infinity, okay? And then this one can be identified with space of polynomials of one variable z. Z is a variable of coordinate of c of a degree less or equal to 2L, okay? So then this cohomology is become a very concrete space. It's just a polynomial of degree up to certain number, okay? Then the standard metric this time is this is just spherical metric, and any other metric must be of a form of this, okay? So here I write this way. There are few ways of writing a metric in a conformal class, but I want to write this way because I want to stay in the Kähler class, I'm doing a Kähler deformation. So this time I want 1 plus Laplace phi. And this, of course, 1 plus Laplace phi is positive. Okay? So Laplace is the Laplacian of this fixing. So function is any function. Okay? In any function such that this is positive. Okay? So then you have a whole this set of functions such that this is basically you have a whole set of these functions such that 1 plus Laplace phi is positive. So phi is defined on the S2. We can think it's a function on the C, and such that there are certain asymptotic conditions at infinity. Okay, so then what I look at these things here in our this thesis. So this basically says this is written as the following. Okay, and this is a polynomial, and the polynomial, because orthogonal condition you have this is a basis. Orthogonal condition is like this. So this, if I fix omega or I fix phi, what I proved in thesis says as L goes to infinity, this will goes to zero. Okay, will goes to zero, and or goes to some constant. I'm sorry. So goes to some constant and subject to this condition. So then the partial zero simply says if you impose this actual condition in addition to this, so this is like curvature bounded from below by some positive constant, which is 1 plus kappa. Okay, and then this one has a uniform low bound. So this one has a uniform low bound. Okay, so this is if you look at here, this is maybe you can think as is a different way of formulating a Weierstrass theorem. So Weierstrass theorem, any function can be approximated by polynomials. But I didn't do exactly in terms of polynomial. In terms of there's an algorithm and things here. Okay. But again, this is approximated by any function can be, and this subject to this condition can be approximated by polynomial this way. Okay. So then you expect some uniform things. Actually, I think this can be proved in this particular case, though I haven't worked out things. And not only this time you can have a low bound, I also think this one actually probably in the weak norm goes to constant. Okay, in some should be some uniformity holds in a much stronger sense. So now we're back to this conjecture. So if this conjecture, what I mean is this general case, if this conjecture is true, then the probabilities of f omega 0 along the O bounds continuous method follows from the case stability. And the reason for that because this conjecture tells you if you apply to this Monchampy equation you want to solve, for any solution you can approximate by certain polynomial defined functions, a logarithm of polynomial defined functions, and then that's become a finite dimensional case. And the probabilities I said, roughly speaking, is like probabilities of this Lagrangian restricted finite dimensional case. So use that to get the bound. Okay. So however, this is in general case this conjecture is still open except for Kähler-Einstein matrix, which is not enough to complete O bounds method, O bounds continuity method. So maybe I skip this. So in the 210 or maybe 210, 211, Donaldson suggested a new continuity method by using a so-called conic Kähler-Einstein matrix. So namely, if you consider more general Kähler matrix, okay, but it's not too general. This is the Kähler matrix of the following type. You start with the Kähler manifold. You take a divisor, which is say this time for simplicity, just take a divisor to be a smooth divisor, and the conic Kähler matrix on M with angle 2 pi beta is between this. This is not absolutely necessary, but there's some geometric meaning for this. At least it's enough for our case. Along the D is a Kähler matrix, a smooth Kähler matrix on the complement, and asymptotic equivalent along the D is to the modal matrix. So you look at this modal matrix. This one has singularities, and this is smooth. So this in the normal direction of D, it has singularities, but it's not too bad. It's still, for example, LP bounded for some p bigger than 1. So basically, this metric Y is a conic. If you write in terms of polar coordinates here, this metric looks like this. This is D, and in the normal directions, it's like a conic, and this cone angle is 2 pi beta. 2 pi beta. Okay, if you can immediately see that if you rewrite this part in terms of polar coordinates in the normal directions. Okay, in the normal direction. So this is not smooth metric, but it's not too far from us being smooth, and then you can this just says you can do all these cohomological things like you can have a Kähler class and so on, and you can also consider conic Kähler-Einstein metric. So this is a conic Kähler metric which also ends outside conic points, and this one here is just a delta function along the divisor. So outside divisor, this is exactly this Einstein equations. Mu is a constant, and in our case, mu is positive. So this D is delta function because the metric has a singularity along the D, so its curvature has certain concentrated contributions. That's delta, like delta functions. Okay, so this is not really an equation. It's like just globally. As some generalized function is defined this way. So in 211, there were a lot of works. So the Simon Brandl did a Ricci-flat case, conic established basically proved a version like analogy of Calabi-Yau theorem for conic Kähler-Einstein matrix, but with cone angle less equal to pi. So that means beta less equal to half. Okay. So this is an unwanted constraint, but this is one of the existing theorems. And then Jeffrey and Mazel and Rubinstein, around the same time, they established a more general case. They prove the existence of a conical Kähler-Einstein matrix with non-positive scalar curvature. Okay? And they also have a result in the case of positive curvature. So this is basically they also have generalized my theorem for smooth Kähler-Einstein matrix to a conical Kähler-Einstein matrix. So, so that means if a certain function is proper, then there's a conical Kähler-Einstein matrix in the positive case. So in the positive case, in general, you have abstractions. Okay? And there's a case stability and so on. There are also related work by Campana and so on. And they did a more general case. They consider the device which is not necessarily smooth, only normal crossing, but they got less information of a metric along the devices. So what they did was not necessarily useful. I mean, it's not useful in our case because we need precise information on our devices. Okay. So the original suggestion of Donaldson to start with a smooth anti-canonical case. Maybe I do quickly because of time. So unlearn every fellow manifold admits this. So there are some modifications. So basically, this modification is at the beginning, and the device D has certain constraints, and this constraint is not necessary. It's not necessary. Okay. So then Donaldson continuous method can be stated as follows: you let E to be a set of beta, such that in this range, and why in this range? Because lambda is some given constant determined by device D. And in this thing, you want to stay in the positive scalar curvature case. So E set such that there is a conical Kähler-Einstein metric. It should be conical Kähler-Einstein metric. Sorry, and it turns out the beta is in if beta is sufficiently close to this. Okay, so that's due to Jeffrey, Mazel, Rubinstein, and Bowman, and also using some result of Bowman. And so E is open. That's proved by Donaldson. So as I said, a valid continuous method. This is crucial. So open is very important for having a valid continuous method. So that's why we call this continuous. So this Donaldson continuous method, and this method does play a crucial role in establishing existence of Kähler-Einstein matrix. So the beta is that if twist is some energy is a functional Lagrangian is proper. So this is so again we remains to prove E is closed. E is closed. Okay, the open is known and E is non-empty. So again, as before, we need to prove this is closed. And then by same arguments, one can extend the Fataki invariant to log Fataki invariant, namely to the conical case. Everything in what we did the smooth case can be generalized to the conical case. And it's further observed. If M is K-stable, so does this for any beta in this range. So there's some monotonicity here. If it's M is K-stable, that corresponds to case when the beta is 1, then it's, for smaller beta it's also stable. It's so stable. Okay. So then this, again, it's like in the Aubin continuous method, the key in completing a Donaldson's continuous method is to establish a partial zero estimate. The partial zero estimate is exactly the same as I said before, because in the conical case, even though metric has singularities, but it does not have too bad singularities. So it's so you can still define a partial C0. So you can still make sense of these density functions and so on. Okay. Only thing the norm here is not necessarily smooth. It's only a whole continuous norm because of conical singularities. Okay. So then the conical version of partial zero is the same. Is stated exactly the same. So but this time we allow the metric to be this, and for our purpose, I only consider the Kähler-Einstein case. So we want this to be bigger to 0 because these continuous methods are confined to a conical Kähler-Einstein matrix. So we only want this to be a conical Kähler-Einstein. Okay, and this is actually a special case of previous the general conjecture, because any conical Kähler-Einstein matrix can be approximated by a smooth Kähler matrix with the Ricci-Cauchy boundary from below by its right numbers. So then the crucial technique for establishing partial C0 is the extension of Kähler coding and myself's compactness theorem to conical matrix. Because in the smooth case for Kähler-Einstein matrix, why in general case we cannot do it, we can do for Kähler-Einstein case, that's because one of the key technical ingredients is this compactness theorem I established with Jeff and Toby. So to do extension, I just summarize. So to do this extension, we need to use the approximation theorem I proved for conical Kähler-Einstein matrix, as well as my joint work with Bing Wang, one of my former postdoc in Princeton 2 years ago, and some actual ingredient about the smooth convergence. Okay. So once we have an extension, by using an error-to estimate for D-bar operator, we can establish partial C0 for conical Kähler-Einstein matrix. So the path to establishing a partial C0 for conical Kähler-Einstein matrix is the same as what we did for Kähler-Einstein matrix. Okay. And the only thing, the key part that took a last step, basically, last block is try to extend the Kähler coding Tian. It's the extension. And this compact theorem, which is by no means is non-trivial because there are certain arguments in the previous case depends on smoothness of things. Okay. So giving so with this partial C0, then with partial C0 and this discussion about extension of case stabilities to conical case, then you can complete the proof of a theorem I stated previously. So namely, if a manifold is case stable, then there's a Kähler-Einstein matrix. That's Kähler-Einstein matrix. Of course, this is case stability is also necessary condition. So in the last few, I just make a few remarks about a more recent work. It's giving a final manifold. It's hard to check if it is case stable, even though the case stability is only a algebraic condition. So the previous theorem is only an equivalence theorem. It's one hand is solving nonlinear equations. On the other hand, there are some stability condition, which is algebraic condition. And what we prove is these two things are equivalent. These are equivalent. And the key issue is to have this some strong estimate, right? So we call it partial C0. So however, the case stability condition is case stability is still hard to check, even algebraic, right? It's like you can approximate the functions, continuous function by polynomials, but if you want this approximation to have certain properties, it's still a difficult question. Okay? So there's another approach to establish existence. So this is approach was given by Kähler-Ricci flow. So you consider normalized Kähler-Ricci flow of so that's a Hamilton-Ricci flow in the Kähler case. The Carl proved in '86 that this flow has a global solution. Okay. He also did for other cases, namely the lambda. There's a lambda in front of that. So that's just confined to a lambda equal to 1 case. So the problem is to show what is the limit of this omega t as t goes to infinity. Okay. So in general, you don't expect a limit because I said that there are abstractions. So because I may not have a limit as t goes to infinity. Okay? So there was a conjecture says if m omega t always converges to generalize the Kähler-Ricci soliton in the Kähler-Gromov topology. So this space may be different from that space, but they are very closely related. Okay, and this convergence in a certain topology, this is let's say called Cheever-Gromov. Okay, so this is topology is only convergence outside the singular set. So here this M infinity is only it's not necessarily a smooth space, okay, and it's smooth outside the closed subset of Hausdorff codimension at least 4. Okay, see, in fact, now we can prove this subset is subrighted, and M infinity is subrighted too. That's again is a consequence of this partial C0 estimate. That was known for a long time, even in my expository paper. So the rule, and actually the partial C0 estimate gives a lot, and particularly implies the regularity of M infinity in the sharp form. Okay, so and M omega infinity is a smooth scalar metric on the regular part of this, and satisfies this equation. This is a Soliton equation. So because of this side you can write as a Hessing of U. Okay, so it's known this conjecture implies the previous conjecture, because if M is k-stable, then you can make sure this final Kähler-Einstein Soliton will stay in the original manifold. So what I mean here is a k-stability assures M infinity in this new conjecture coincides with M, and G infinity is Kähler-Einstein. Okay. So there are some supporting evidence which I will skip that, and various conditions. So what recently and Zhenrui Zhang and I solved this conjecture for dimension less equal to 3. So namely, if dimension less equal to 3, then this one converges to a generalized Kähler-Einstein Soliton, and moreover, M infinity is a normal right, as I said. So you might ask, why is dimension less equal to 3? But that's because there are some. So what we actually proved is if a Ricci curvature along the Kähler-Ricci flow is LP bounded for certain p bigger than half of a dimension, then you have everything. You can get everything, and unfortunately, we can only establish that LP condition on the Ricci curvature along the Ricci flow for p equal to 4. So that covers dimension less equal to 3. So hopefully we can do better. And this announcement of this paper already published, just recently accepted and stuff. So anyway, so that's what I want to talk to you. Thank you.
Any questions?